Welcome back, everyone. We're going to continue now with the topic of isogenies. So in math, once you've defined a concept like vector spaces or topological spaces, the next item in the list is to talk about maps between those types of spaces. The maps between elliptic curves are called isogenies. So let's define what's an isogeny. An isogeny, so let E1, E2 be elliptic curves. Then a morphism phi from E1 to E2 such that O, the origin, the 0 for E1 is mapped to O for E2 is called an isogeny. If phi of E1 is not just O of E2, so it is non-constant, then we say that E1 and E2 are isogenous. Okay. Great. So isogenous and isogeny. Notice that I'm actually not requiring my isogeny to be a group homomorphism in the definition. That we will prove that it actually comes for free, that they are group homomorphisms. So let me give you a few examples to begin with. So we do have example like, well, we always have the map 0 that sends E1 to E2, right? That sends every point to O of E2. That is an isogeny, but that is like the trivial isogeny, the constant isogeny. Other isogenies, you do have, for example, a multiplication by M from E to E that sends P to M times P. So P plus P plus P M times. This is for some positive M. Those are isogenies. Is that there's the fact that oh, by the way, so something that I didn't actually prove, but which is a theorem in Silverman, is that the maps from E to E, from E cross E to E, that sends that is addition, so P and Q is sent to P plus Q. This is a morphism. And the map that sends E to E, that sends P to minus P, this is also a morphism. So then multiplication by M, which is just the repeated composition of addition, will also be a morphism, and it sends 0 to 0, so it is an isogeny. Okay. There are other examples of isogenies. Let me pick up a couple of examples from my notes. Here is another example, a little bit more exotic, but also very important. So you can go, if you have an elliptic curve, let's define E1 to be an elliptic curve of this particular shape, y squared equals x cubed plus ax squared plus bx. So this is a not a short Weierstrass form, you see that there is a x squared term, so it's a long Weierstrass form, but it's missing a few of the coefficients. And I'm going to define E2 to be y squared equals x cubed minus 2ax plus a squared minus 4bx. And this quantity, I'm going to call it R. Then it turns out there is a map from E1 to E2 that sends xy to y squared equals x squared over and then comma b minus x squared over x squared. Okay, and this is an example of what's called a two-isogeny, which much later will be very useful to actually do the a type of descent, which is a method to compute the Mordell-Weil group of an elliptic curve. It turns out that this one has there is a map in the other direction. There is a map that we're going to call phi hat from E2 to E1 such that xy maps to y squared over 4x squared, comma y r minus x squared over 8x squared. And it turns out that the property that these two maps have, an interesting property, is that it turns out if you compose them or compose them in the other way, you get in both ways, you get the multiplication by 2 map. There, the multiplication by 2 map is in different places. So this one starts on E2 and ends in E2. So this is going from E2 to E2, if I get that right. And phi starts in E1. So this is going from E1 to E1. So multiplication by 2 on E2 on E1. So they're not inverses of each other, but their composition gives you another isogeny, which is multiplication by 2. This will be key in the theory of isogenies, that it turns out there is always this other isogeny that goes in the other direction that is called the dual isogeny. We'll get there. All right, so those are some examples of isogenies. Remember the degree of a map, how we define it. So if phi is an isogeny, we define the degree of the isogeny like we did the degree of maps before, which is the extension. So phi is an isogeny from E1 to E2, the isogeny of elliptic curves. Then we defined the degree of the isogeny like we did before for degrees of maps as the extension of function fields. And we actually define the degree of a constant isogeny. There's only one constant isogeny, the map that sends everything to 0. So it's the degree of a constant isogeny, which is the degree of the 0 map, that we define it to be 0. Okay, great. So, so now what we're going to prove is that isogenies, which were not by definition homomorphisms, they are actually homomorphisms from free. So if I have a morphism that sends 0 to 0 between elliptic curves, it is actually a group homomorphism. Let's try. Okay, so let phi from E1 to E2 be an isogeny. Then phi of p plus q is phi of p, plus phi of q for all p and q on E1. Right, so here's the proof. If the isogeny is constant, then this is clear because 0 plus 0 equals 0. Okay, then this is clear. So we're going to assume, otherwise, we're going to assume that phi is a non-constant isogeny, in which case is there is a finite degree to the isogeny, which we call this is a finite map. Okay, some finite map, and let I'm going to define a map phi lower star from the Picard group of E1 to the Picard group of E2, okay, such that the class of the sum of ni times pi of this divisor is just going to be sent to the class in Picard of the sum of ni phi of pi. Okay, but now remember, so Picard is isomorphic to E1. That's something we proved last time. So recall that the Picard group is isomorphic to each EI. By the way, this is well defined. Note here that this is well defined we need to know that principal divisors go to principal divisors. So it turns out that that is true because phi lower star of the divisor of a function f is the divisor of a function. It is the divisor of phi star of f. But that phi upper star is not the phi star that we already defined. We haven't defined actually this upper phi star, but you can find it in the book. I'm just telling you that there is some other function phi star of f that this phi lower star of the divisor of f is a divisor of a function. Okay, so I'm not going to go into that, but that is true, that this is actually a well-defined map. And this gives me a diagram that I have E1, which is isomorphic, remember, via kappa. So we had a sigma that went from Picard to E, and we have a kappa that goes from E to Picard. But in any case, there is an isomorphism from Picard 0 to the elliptic curve, and I have a map phi that goes to E2, my isogeny. I have a phi star, phi lower star, that goes to Picard of E2, and this is also an isomorphism here. Okay, and this diagram actually commutes. It commutes because, well, it sends P, maybe, well, yeah, P sends, remember, it goes in one direction. P goes to Picard as the class of P minus O. Phi star would send this to the class of phi of P minus a class of phi of O. Okay, but phi is an isogeny, so it sends O to O. So this is the class of phi of P minus the class of O. Okay, let's go in the other direction. This would send P to phi of P, and then the kappa for E2 would send actually phi of P to the class of phi of P minus O. So the diagram commutes. Okay, so now I have that diagram. I'm going to use the diagram to prove that phi of P plus Q is phi of P plus phi of Q. So I had a diagram E1 let's draw that correctly. E1 to Picard through phi lower star to Picard for E2, and I have E2 here, and I have the isogeny phi, and this diagram commutes, right? So now let's see what happens if I start with P plus Q on the upper left corner. That is going to be mapped to P plus Q minus O, or the class of, okay, of that. But we actually remember, if you remember the proof of when we proved that Picard's 0 and E are isomorphic, that the Picard group on the elliptic curve, there is an isomorphism between the two, we showed that P plus Q, let me actually write it. I don't think I should write it up here. Write it here. We showed that P plus Q minus P minus Q plus O was the divisor of a function we called f prime over f, and therefore equivalent to 0. And this told me then that P plus Q minus O is equivalent to P minus O plus Q minus O. That was, we proved that to prove that kappa of P plus Q equals kappa of P plus kappa of Q. What that tells me is that that P plus Q minus O is equivalent to P minus O plus Q minus O in Picard. Okay, and then if I see where does this map, this part would map to phi of P plus Q minus O, but these ones would map to phi of P minus O plus phi of Q minus O. And then if I go in the other direction of my commutative map, this goes to phi of P plus Q. Okay, and this is an isomorphism here, and then we see that these two these have to map to so this, which is equivalent to the sum of these two, have to map to the same place, and they have to map to phi of P plus phi of Q. Okay, these map there. So therefore, these two things have to be the same, and phi of P plus Q equals phi of P plus phi of Q. So phi, if it's an isogeny, a morphism that sends 0 to 0, it is also a group homomorphism of elliptic curves. Great. All right, so now one corollary of that is that if phi from E1 to E2 is an isogeny, then the kernel, now that we know it's a group homomorphism, I can call it the kernel, which is phi minus 1 of O, the points that map to O, is a finite subgroup. Of E1. Let's say that this is an isogeny, a non-constant isogeny. And in particular, the size of the kernel is less or equal to the degree of phi. We will actually see that it's equal in a moment. But for now, we can just prove this because we have a group homomorphism now that we just need to count what is phi minus 1 of O. And remember that we have a formula that P in phi minus 1 of O for any Q, but for O in particular, we have a formula that tells me that the degree of a function is the sum of ramification indices of points in the preimage of O. But then this is either, so that this implies that at most, the largest this can be, so the largest this can be is when all the ramification indices are 1, but in that case, I get, or the largest amount of points in the preimage of O is when all the ramification indices are 1, in which case I get degree of 5 points. So in all cases, this is less than the degree. If it was more than the degree, then there would be more. That formula wouldn't work. Okay. So now we're going to have a few definitions about homs and things like that. Okay, so first of all, we have a group of isogenies. So let E1, E2 be elliptic curves over K. Then first hom from E1 to E2 is the set of isogenies that go from E1 to E2. And it turns out that this is a group that's easy to check, that the homomorphisms from E1 to E2 is a group under addition. So that if you have an isogeny phi and isogeny psi, then if you want to know what the new isogeny, the addition isogeny does, it just sends P to phi of P plus psi of P. Because now we know that there is well, we have an addition on E2 that makes that work. Great. Now the endomorphisms from E to E. The endomorphisms are always from E to itself, so we don't need to write the second E. The endomorphisms of E is the group of homomorphisms from E to E. So isogenies from E to itself. Okay. In this case, end of E is a ring. Is a ring under addition, like all homes, and composition, where phi times psi of P is going to be the composition of phi and psi. So first apply psi, then apply phi. Okay. Notice that I do get a new hom from E to E if I compose, but the composition does not necessarily need to be commutative. And in some cases, it will not be commutative. Okay. There are, we already have seen examples of endomorphisms. I'll give a few more examples in a moment. So then we have automorphisms of E. These are the invertible elements in endomorphisms. So the endomorphism from a ring, and some will be units, some will not be units. Those that are units in the ring that are invertible, those are the automorphisms. So these are the invertible elements of endomorphisms. Okay. And we can do all of these are just isogenies. They are defined over K bar. But if they are defined over K, this is a morphism. So defined over K means that the polynomials that define the morphism are defined over K. And then those are homs defined over K. So we can have homs defined over K and endomorphism ring defined over K and automorphism ring over K and so on. Okay, so let me write some examples here. We have already seen that we have multiplication by M is a addition is a morphism. So multiplication by M is a morphism. And it is going from E to E. So it's an example of an endomorphism that sends P to M times P. So P plus PM times. So then M is an endomorphism. And then this is for M bigger than 0. If M is negative, inversion, so minus is also an endomorphism. I mean, it's also a morphism, so I can instead I can define M times P with M negative to be minus M, which now minus M would be positive, which is one of the ones above, times minus P. Okay, so I can find first minus P and then add that one M times. So this is minus P plus minus P plus minus P M times. And notice that, again, minus is a morphism and multiplication by M is a morphism. So now this is all a morphism also. Let me give you something that is not on a multiplication by M map as an endomorphism. So there's a whole theory of isogenies and endomorphisms, and in particular, these are very important here, the endomorphisms that are other than multiplication by M for a map. So for example, if I have E to be x cubed minus x, then there is an extra endomorphism that we're going to call I, and it sends xy to minus x comma iy. You see that if I replace x by minus x, then the right-hand side quantity is multiplied by minus 1, And then if I multiply the y by I, when I square, I get also -1, and this becomes an endomorphism. So this is an endomorphism. So I also belongs to the endomorphisms of this particular elliptic curve E. So this is a very particular endomorphism that appears in that elliptic curve, but it's not something that I can do for just any elliptic curve. We'll see. We'll talk more about elliptic curve with these sort of like extra endomorphisms in a moment. Right. Let's prove something about endomorphisms and homs. So this is proposition 4.2. A. The multiplication by M map is non-constant. On EK bar for all integers M that are non-zero. Okay. For any non-zero integer M, that is a non-constant morphism or a non-constant isogeny. B, the homs from E1 to E2, this is actually a torsion-free Z module. Okay, so we are going to show that there is no torsion. And C, the endomorphism ring of an elliptic curve is a ring of characteristic 0 with no zero divisors. But not necessarily commutative. Okay, so how do you prove something like this? First of all, the fact that M is non-constant is because we can actually, I'm not going to do this, but you can use explicit formulas. You can using explicit addition formulas, we can actually compute. We could find x of p times q, say for p a prime. So let p be a prime. We could find the formula for multiplication by p. I gave in the last lecture, I gave the formula for multiplication by 2. So you could do for multiplication by 3, you just have to keep adding, and then you would find multiplication by any number. But you can do, for example, for primes, you can find formulas for the x coordinate, and you can find a formula for the y coordinate. And those are given by rational functions in terms of the coefficients of the elliptic curve. And thus, I can find points of order p. So I can find points such that these two, the x, when I multiply by p, I get O. I get the point at infinity. So so I can use those formulas to find points of order p. For any prime p. Okay, maybe call this q, since we have already a p floating around. So I can always find points of order p. Okay, so therefore, if there are points of order p, then the map M is not going to be a constant function, we are going to have points that are of order p, and or points that are under multiplication by m are not of order p. All right, great. So now for B, I want to show that the map is, the homes are torsion free. So suppose that I have an isogeny. Okay, and I have some integer, and I want to see if I can create a torsion element. So something that m times this element gives me 0. M times means if I'm going to multiply this by m, it is a z-module because I can just add phi m times. And what's happening is, so m times phi is really the composition of multiplication by m with phi. Okay, so that makes it into a z-module. And if this was torsion, then I would have that after multiplying by m, I get the 0, I get a constant map. Okay. Then if I take degrees, remember that the degrees are multiplicative in towers. So the degree of the composition is the degree, is the multiple of the degrees. And the degree of the constant map is 0. Okay. But now these are integers. And if the two are 0, then either this is 0. So either the degree of m is 0, but that is constant only when m is 0. So m is 0, or the degree of phi is 0, in which case phi is constant, and then phi has to be 0. Okay, so the only way that you could have torsion is if your map phi is already 0, or you're multiplying by 0. So there is no torsion. So HOMS from E1 to E2 is torsion free as a Z module. And for part C, well, from B, I already see that the endomorphism ring, which is HOMS from E to E, this has to be of characteristic 0, because if it was of characteristic P, there would be torsion, right? So now I need to show that there is no 0 divisors. So if I had a 0 divisor, that would mean that I multiply two endomorphisms and I get 0, so I get the 0 endomorphism. But then this says in terms of degrees, again, the degree of phi times the degree of psi is the degree of the composition, which is 0, of the degree of a constant map. But then again, this says that either the degree of phi is 0, which makes phi be the 0 map, or the degree of psi is 0, which makes psi be the constant map. So in either case, this tells me then that endomorphisms is an integral domain. As I wanted to prove. Okay. Great. All right. So very good. So now let me define There's a couple more things, and maybe I'll stop. We define the M torsion of an elliptic curve. So for an integer m, we define the M torsion to be those points on E such that M times P is O. Okay. And this is what we call, so this is over K bar. Okay, so any point over K bar, so this is over K bar. Those are the points that will go through after multiplication by M. They give you 0. We can also define EK of M. So those points that are defined over the base field such that multiplication by M gives me O. And this is contained in the M torsion, but it's not necessarily the same. And in most cases, it is much smaller. So for example, if you're talking about Q, there's very few times where you can have, so it turns out that you can only have the full M torsion defined over Q if M is 2. If M is 3, you cannot have a full 3 torsion defined over Q. So there's always 3 torsion points that are defined over the algebraic closure of Q. And we are going to call the torsion is the entire torsion subgroup of the elliptic curve. So is the union for M1 up to infinity of the M torsion subgroups. Okay, so that is the largest torsion subgroup. Okay. Let's see. So let me also just define, while we're talking about endomorphisms, one more thing, which is that, so first note that the multiplications by M maps that this is an injection. So that the map that sends each M to in here, so each M gives me multiplication by M, that this is an injection. Why is that? Because we've proved there's no torsion there, so we can't have that multiplication by M be 0. So if there is some repetition, then we would have some multiplication by M map that is constant, but that doesn't happen. So we have an injection in there. So what this means is then that you can consider the integers are always inside the endomorphism ring of E. But sometimes this is not always the case that it's exactly the same. So if the integers are contained but not exactly equal to the endomorphisms of E, then we say that E has complex multiplication or that E has CM. Okay, the theory of complex multiplication is very rich, but it is sort of an advanced topic, and in fact, in the second volume of Silverman on the advanced topics in the arithmetic of elliptic curves, there is a whole chapter, a long chapter dedicated to elliptic curves with CM, with complex multiplication. We've seen an example of an elliptic curve with complex multiplication that was, let me use some other color here. We've seen an example, which is E. This elliptic curve has, what are the endomorphisms? Well, on one hand, we have all the multiplication by M maps. Okay, and on the other hand, we saw the an extra endomorphism that sends xy to minus x comma iy. So this one is also here. And it turns out that the endomorphism ring for this elliptic curve, it is actually isomorphic to z adjoint I. So we have maps for every a plus bi. In here, we have a map multiplication by a plus multiplication by I composed with multiplication by b. And those are all the endomorphisms on my elliptic curve. Okay, and then we say that E has Cm by z adjoint I, because that is the shape of the endomorphism ring. Okay, and there is, for every quadratic imaginary field, if you take an order in one of those, so take the maximal order, which is the ring of integers, or take an order, a suborder of the ring of integers, there is an elliptic curve, not necessarily over Q, but an elliptic curve that has complex multiplication by that ring, in that the endomorphism ring is isomorphic to one of those orders. And it's a beautiful theory, but a little bit complicated and beyond the scope of this first course on elliptic curves. Okay, so I'm going to stop here for now, and then I'll talk a little bit more about isogenies in the next video.